Running a single 2-inch conduit to a junction box on each floor and branching into each apartment is feasible if the following conditions are met. Firstly, the feeder wires for each panel can fit within the conduit with adequate fill space. Secondly, the junction boxes are large enough to accommodate the splices and terminations for all the feeders. Thirdly, the conduit is installed in a manner that allows future access for maintenance and repairs. Benefits of a single conduit include reduced material cost. Using a single conduit is more economical than running separate conduits for each apartment. Less labor is involved because installing a single conduit requires less time and effort compared to multiple conduits. Improved aesthetics are possible because a single conduit can be concealed in the drop ceiling, providing a cleaner appearance. Drawbacks of a single conduit include limited flexibility because it may be more difficult to reconfigure or expand the electrical system in the future if all the feeders are contained in a single conduit. Maintenance challenges can arise because if a problem occurs with any of the feeders, it may be necessary to shut down the entire electrical system for repairs. Potential code violations could occur because some building codes may require separate conduits for each apartment. If the aforementioned conditions are met and the benefits outweigh the drawbacks, running a single 2-inch conduit to a junction box on each floor and branching into each apartment is a feasible option. However, if there are any concerns about flexibility, maintenance, or code compliance, it may be preferable to run separate conduits for each apartment. Additional considerations must be made for load calculations. Ensure that the feeder wires in the conduit have sufficient capacity to handle the maximum load for all the apartments on that floor. Calculate the conduit fill to ensure there is adequate space for the wires and any future additions. Select junction boxes that are large enough to accommodate all the splices and terminations neatly. Use wire ties or other methods to organize the wires within the conduit and junction boxes. When working on electrical projects, you must comply with the National Electrical Code, or NEC. Article 230 covers service entrances. Article 300 covers wiring methods. Article 310 covers conductors for general wiring. Article 314 covers outlet device, pole, and junction boxes, conduit bodies, fittings, and handhole enclosures. Article 334 covers non-metallic sheathed cable. Article 344 covers rigid metal conduit. Article 352 covers rigid polyvinyl chloride conduit Schedule 40, Schedule 80, and Type EB. Article 358 covers electrical metallic tubing. Article 370 covers cable trays. Chapter 9 contains tables and examples. For conduit fill, refer to Chapter 9, Table 1, and the notes to the tables. These provide guidance on the maximum allowable percentage fill for conduits. Always consult the latest edition of the NEC and local amendments for specific requirements in the jurisdiction. Regarding wire sizing, several factors determine the appropriate size for electrical wires. These include the ampacity of the circuit, the allowable voltage drop, and the ambient temperature. The ampacity of a wire is its current carrying capacity, which is the maximum amount of current, measured in amps, it can safely carry continuously without overheating. The NEC provides tables that list the ampacities of different wire sizes and insulation types. For example, Table 310.15b16 in the NEC lists the ampacities of insulated conductors rated up to 600 volts in raceways or cables or installed directly buried, based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause lights to dim, motors to run inefficiently, and other electrical equipment to malfunction. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where volts drop is the voltage drop in volts, K is the direct current constant, which is 12.9 ohms for copper and 21.2 ohms for aluminum, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. Ambient temperature is the temperature of the environment around the conductor. Higher ambient temperatures reduce the ampacity of wires because they impede heat dissipation. The NEC provides correction factors to adjust the ampacity of wires based on ambient temperature. These correction factors are found in Table 310.15b2 of the NEC. After determining the ampacity, allowable voltage drop, and ambient temperature, you can use the following steps to select the appropriate wire size. Firstly, determine the minimum ampacity required for the circuit. This is typically the load plus 25% for continuous loads. Secondly, adjust the ampacity for ambient temperature using the correction factors in Table 310.15b2 of the NEC. Thirdly, calculate the voltage drop using the voltage drop formula mentioned earlier. Fourthly, select a wire size that has an ampacity equal to or greater than the adjusted ampacity and that will keep the voltage drop within the allowable limits. Remember to consult the latest edition of the NEC and local amendments for specific requirements in the jurisdiction. For a 60 amp panel, you'll need to select a wire size that can handle at least 60 amps continuously. Based on the NEC Table 310.15b16 for 75 degrees Celsius rated conductors, which is a common rating, you would typically use at least a number 6 American wire gauge or AUG copper conductor or a number 4 AWG aluminum conductor. However, this is a simplified example and does not account for voltage drop, ambient temperature corrections, or other factors that may affect the required wire size. Always perform a complete load calculation and voltage drop calculation to determine the appropriate wire size for your specific application. Also, consider the terminal temperature ratings of the breakers and panels. The NEC requires that conductors be sized based on the lowest temperature rating of any connected termination. A typical small apartment electrical system, the main components include the service entrance, distribution panel, branch circuits, and grounding system. The service entrance is where electrical power enters the apartment from the utility company's grid. It typically consists of service conductors, a meter, and a service disconnect. The service conductors are the wires that connect the utility company's transformer to the service disconnect. The meter measures the amount of electricity consumed by the apartment. The service disconnect is a switch or circuit breaker that can be used to disconnect the apartment's electrical system from the utility company's grid. The distribution panel, also known as the breaker box or load center, is the central point for distributing electricity throughout the apartment. It contains circuit breakers that protect individual circuits from overloads and short circuits. The distribution panel typically has a main breaker that can be used to disconnect the entire apartment's electrical system. Branch circuits are the individual circuits that supply power to lights, receptacles, and appliances. Each branch circuit is protected by a circuit breaker in the distribution panel. Common branch circuits in an apartment include lighting circuits, receptacle circuits, and appliance circuits. The grounding system is a network of wires and grounding electrodes that provides a path for fault current to flow back to the source. This helps to protect people from electric shock and prevent damage to electrical equipment. The grounding system typically consists of a grounding electrode conductor, a grounding busbar in the distribution panel, and grounding wires that connect to metal enclosures and equipment. The NEC requires that all electrical equipment in an apartment be properly grounded. For a small apartment with electric heat, the following is a sample load calculation. Lighting load: calculate the lighting load at 3 volt amps per square foot, according to NEC 220.12. For a 1000 square foot apartment, this would be 3000 volt amps. Small appliance circuits are required to have at least 220 amp small appliance circuits. Each circuit is rated at 1500 volt amps according to NEC 220.11 and 210.11 current. This totals 3000 volt amps. The bathroom circuit is required to have 120 amp bathroom circuit rated at 1500 volt amps according to NEC 210.11c3. The heating, ventilation, and air conditioning, or HVAC, unit is rated at 30 amps at 240 volts. This is equivalent to 7200 volt amps. Total volt amps is the sum of all the loads, which is 3000 plus 3000 plus 1500 plus 7200, totaling 14,700 volt amps. Demand factors might be applicable. For dwelling units, NEC 220.42 allows a demand factor of 3 volt amps per square foot for the first 3000 volt amps and 35% for the remainder. The first 3000 volt amps is taken at 100%, which is 3000 volt amps. The remainder is 14,700 minus 3000 equals 11,700 volt amps. At 35% equals 4,095 volt amps. The total demand load is 3000 plus 4095 equals 7095 volt amps. For the 240 volt 8-track unit at 7200 volt amps, dividing by 240 volts gives you 30 amps. For the 120 volt circuits, you have 7095 total volt amps minus the 7200 volt amps for the 8-track unit equals negative 105 volt amps. This would be covered by the 8-track unit. The service size will depend on the calculated load. In this case, a 60 amp service at 240 volts would likely be sufficient, but a larger service may be required if there are other significant loads. This is a simplified load calculation and does not account for all possible loads. It is essential to consult the NEC and perform a complete load calculation before installing any electrical equipment. For the types of electrical boxes, there are several common types of electrical boxes used in residential wiring, each serving a specific purpose. Outlet boxes are used to mount receptacles, switches, and light fixtures. They are typically made of plastic or metal and come in various shapes and sizes. Junction boxes are used to join multiple wires together. They are typically larger than outlet boxes and are required to be accessible. Switch boxes are specifically designed to mount switches. They are similar in size and shape to outlet boxes but may have different mounting options. Ceiling boxes are used to mount light fixtures to the ceiling. They are typically round or octagonal and are designed to support the weight of the fixture. Extension rings are used to increase the depth of an existing electrical box. They are often used when adding new wiring to an existing circuit. The NEC specifies the minimum size and type of electrical box required for each application. The size of the box depends on the number and size of the wires that will be installed in the box. The type of box depends on the location and environment in which it will be installed. Metal boxes are typically required in locations where they may be subject to physical damage. Non-metallic boxes are permitted in dry locations. The NEC also specifies the methods for supporting and securing electrical boxes. Boxes must be securely fastened to a structural member of the building. The conductors entering the box must be protected from abrasion. For wiring methods, there are several common wiring methods used in residential electrical systems. Non-metallic sheathed cable, or NM cable, is the most common type of wiring used in residential construction. It consists of 2 or more insulated conductors enclosed in a non-metallic sheath. NM cable is relatively inexpensive and easy to install. Electrical metallic tubing, or EMT, is a thin-walled metal conduit that is used to protect wires. EMT is more expensive than NM cable but provides better protection against physical damage. Rigid metal conduit, or RMC, is a thick-walled metal conduit that is used in areas where there is a high risk of physical damage. RMC is the most expensive type of wiring but provides the best protection. Flexible metal conduit, or FMC, is a flexible metal conduit that is used to connect electrical boxes to equipment that may vibrate or move. FMC is also used in tight spaces where it is difficult to install other types of conduit. The NEC specifies the allowable uses and restrictions for each type of wiring method. NM cable is not permitted in wet or damp locations. EMT is not permitted in hazardous locations. RMC is required in some hazardous locations. When planning your apartment wiring project, it's crucial to adhere to electrical codes and safety standards. This ensures the safety of residents and protects the property from electrical hazard. Local electrical codes are based on the NEC, but they may have additional requirements or amendments specific to the area. It's important to familiarize yourself with these local codes before starting any electrical work. Hiring a licensed electrician is highly recommended, especially if you're not experienced in electrical work. Licensed electricians have the knowledge and expertise to perform electrical installations safely and correctly. They are also familiar with local codes and can ensure that your project meets all requirements. Obtain the necessary permits before starting any electrical work. Electrical permits are required for most electrical installations and renovations. These permits ensure that the work is inspected by a qualified electrical inspector to verify compliance with electrical codes. Before starting any electrical work, always disconnect the power to the circuit you'll be working on. Use a voltage tester to confirm that the circuit is de-energized. Wear appropriate personal protective equipment, or PPE, such as safety glasses and insulated gloves to protect yourself from electrical hazards. Use the right tools for the job. Use insulated tools specifically designed for electrical work. This will help prevent electrical shocks and other injuries. Inspect electrical wiring for damage. Before making any connections, check the wiring for any signs of damage, such as frayed insulation or exposed wires. Replace any damaged wiring immediately. Make secure connections. Use appropriate connectors and make sure all connections are tight and secure. Loose connections can cause arcing, overheating, and electrical fires. Follow wiring diagrams and instructions. Wiring diagrams and instructions provide detailed information on how to properly wire electrical components. Follow them carefully to ensure that your electrical system is wired correctly. Test electrical circuits after completing the work. Use a multimeter to test the voltage and continuity of the circuits. This will help identify any wiring errors or other problems. Ground electrical equipment properly. Grounding provides a path for fault current to flow back to the source, helping to protect people from electric shock. Ensure that all electrical equipment is properly grounded according to electrical codes. Label electrical panels and circuits. Labeling electrical panels and circuits makes it easier to identify and troubleshoot electrical problems in the future. Use a permanent marker to label each circuit breaker and the corresponding circuit it controls. Keep electrical panels accessible. Electrical panels should be easily accessible for maintenance and repairs. Do not block or obstruct access to electrical panels. Avoid overloading electrical circuits. Overloading electrical circuits can cause overheating, arcing, and electrical fires. Do not plug too many appliances into a single circuit. Use surge protectors to protect electronic equipment. Surge protectors help protect sensitive electronic equipment from voltage spikes and surges. Plug your computers, televisions, and other electronic devices into surge protectors. Install ground fault circuit interrupters, or GFCIs, in wet locations. GFCIs are designed to protect people from electric shock in wet locations such as bathrooms, kitchens, and outdoor areas. Install arc fault circuit interrupters, or RFCIs, to protect against electrical fires. RFCIs are designed to detect arcing faults, which can cause electrical fires. They are required in many areas of the home, such as bedrooms and living rooms. Maintain electrical equipment regularly. Inspect electrical equipment regularly for signs of wear and tear. Replace any worn or damaged equipment immediately. Keep electrical panels clean and free of debris. Dust and debris can accumulate in electrical panels and cause overheating and electrical fires. Keep electrical panels clean and free of obstructions. By following these electrical codes and safety standards, you can ensure the safety of your apartment's electrical system and protect the residents from electrical hazards.